Okay, we're back, and today, in this lesson, we're going to talk about magnetism and magnetic fields. Magnetism, we're going to talk a little bit about the theory of what makes magnetism what it is, and also we're going to talk a little bit about what magnetic fields look like around magnets. So let's go ahead and get started. And the theory of why objects are magnetic is called domain theory. First of all, you have to remember that electrons have an electric field. Obviously, electrons have a negative charge, therefore they are charged objects and they have an electric field around them. But because they're moving, because electrons are constantly moving around the atoms, they also have a magnetic field around them. And you learned later in the course that moving charges do create magnetic fields. Anyway, because of that, the electrons are moving, they create a magnetic field. So that means that since the electrons have a magnetic field around them, then the atom also has a magnetic field, because the little tiny magnetic fields around these electrons can actually add together and create almost like a tiny, tiny, tiny magnet. Very, very small. And that magnet is what we call a dipole. It's the simplest possible magnet you can have. One dipole, meaning two poles. One north pole, one south pole. That's it. It's the smallest possible component, smallest part you can break a magnet into would be one of these dipoles. Okay? And the domain theory of magnetism is all about how those dipoles interact with each other. So let's take a look at that. Let's take a look at that. The domain theory, all of these little individual arrows that you see, all of these arrows here, are what we call dipoles. And when dipoles are next to each other, when atoms, in other words, have the same little magnetic field around them, a lot of times they can be pointing in the same direction next to each other. And when a bunch of dipoles point in the same direction like this, you got all these arrows pointing in the same direction, we call that a domain. A domain is a group of dipoles that have the same orientation, that are next to each other. And these domains, you'll notice in this piece right here, in this piece of metal, this is just an unmagnetized piece of metal. And if you look around at all the dipoles, all the domains, they're pointing in random directions. They're pointing off in random directions. That means that that piece of metal that you see there in that diagram is not a magnet. Because all of these dipoles and domains, because they're pointing in different directions, the net effect is they cancel each other out. And that's what most materials are like. Most materials are like that. They're not magnets. But if all the dipoles, all the domains line up like they are in this piece down here, that creates a magnet. These little domains, the arrow always points towards the North Pole, by the way. So all these domains, all these dipoles within the domains are all lined up and pointing in the same direction. And that just creates a stronger and stronger and stronger magnetic field. And eventually it's strong enough that we can call it a magnet. So the domain theory helps us explain what makes that magnet. But it also helps explain a couple of other things, like why sometimes a magnet can become demagnetized, or why you should store magnets in a certain way, and things like that. So let's take a look at that. First of all, one way to make a magnet is by putting it close to or rubbing it with an existing magnet. Right? If we take a piece of metal, and metals are usually used for this because metals have domains that can easily be realigned. They move around a little easier because the electrons are easy to move in a metal. But anyway, the strong magnetic field of a magnet close to this piece of metal, or even stroking it, you rub the magnet over the top of it, what happens is that starts to twist the domains around and starts to align them with the magnet itself. And in essence, what happens is the domains in the piece of metal begin to line up. And as they begin to line up, some of them start to grow as well, because these two here, at first, this was two separate domains. There was actually a line down through there, but because now all the dipoles are pointing in the same direction, those two domains actually join together and make a larger one. That's why it says they, not only do they line up, they also grow. So this is what we call an induced magnet. That piece of metal, piece of iron in this case, has become a temporary magnet. Now, if you take the other magnet away, then those domains will begin to snap back the way they were pointing initially. And that piece of iron will lose its magnetic field fairly quickly. And so it's not a permanent magnet. It's what we call an induced magnet. It's only a temporary magnet as long as the other magnet is close. As soon as the other magnet goes away, this tends to get all jumbled up again and it loses its magnetic field. Okay, and you may have noticed that before, like in elementary school, you may have made an electromagnet, and when you start picking up paper clips with that magnet, okay, you pick up one paper clip, and then you can join another paper clip to the end of that one because the first paper clip is touching a magnet. So therefore, the paper clip, because it's made of metal, actually becomes a temporary magnet, and then that one can pick up another one, and so on. You can make a chain several paper clips long just using the magnetic fields, and it's because the paper clips actually turn into temporary magnets while they're touching that magnet. Okay, so let's take a look at the opposite. What about if you take a magnet and you break it in half? Okay, this one is shown up on the public exam in a multiple choice several times, so let's take a look at what happens there. If we snap the magnet in two, we end up with two magnets. Not only do we end up with two magnets, but the poles stay the same. Like, for example, if there was a north pole and a south pole at the left, north pole at the right, and you crack the magnet in half, you might expect these two to be both the same, but they're not. Because when you break the magnet in half, the domains are still pointing in the original direction. And remember, whatever direction the arrows point, that's the north pole. So when you break the magnet in half, you've got a north pole and a south pole right next to each other. Okay, so we got two pieces of magnet now that are basically identical to the original magnet. They're going to be a little weaker because you got a smaller magnet, but because of the domain theory, that tells us that it ends up looking pretty much exactly like the original magnet looked. And we're going to look at a multiple choice like that in just a few minutes. Okay, you can also demagnetize a material in other ways as well. For example, if you drop a magnet several times, it tends to jumble up the domains and the magnet will become weaker. If you store two magnets next to each other and the domains are actually pointing against each other, that's going to weaken the magnets. Because they're opposing each other, that tends to start to turn the domains in the opposite direction to try to make them line up, and that actually weakens the magnet. So when you store magnets, they're usually supposed to be stored all in the same direction. Okay, you set them up so that they're not opposing each other. Okay, in other words, you line them all up side by side. You don't just throw them in a box all kinds of different directions, because if you do that, they'll fairly quick, over time, they will actually lose their magnetic strength. They will actually lose their magnetic field. Heating them up can do the same thing, because when you heat it up, the electrons start to move faster, the atoms start to jump around faster, and that has a tendency also to jumble the domains and make the magnet weaker. Okay, so all those types of things can happen, but it's all explained by the domain theory. It can all be explained by that. Now, a piece of iron, even if it's not a magnet, we still call it a magnetic substance because it has magnetic properties. In other words, it has these domains, and these domains can line up in the right conditions. Okay, some materials don't have these domains at all because the atoms are just spinning in random, or the electrons spinning in random directions, and they don't create these dipoles and domains. Okay, now materials that are strongly attracted to a magnet, and this is important because it could show up as a multiple choice question, you never know. That means they're ferromagnetic. Ferromagnetic materials have strong magnetic properties like iron, cobalt, nickel. Those things are strongly attracted to a magnet. Other metals are not attracted to a magnet. For example, aluminum is not attracted to a magnet. Okay? Aluminum is not. But iron and any type of alloy that contains iron, or cobalt or nickel, does have magnetic properties. Okay? Stainless steel, for example, depending on the composition of the stainless steel, okay, it may have iron in it, it may not. It may have nickel in it, it may not. It depends on how much of these things it has, whether or not it will be attracted to a magnet. Like some stainless steel is, some isn't. Okay? The high quality stainless steel generally is not attracted to a magnet, at least not very strongly. Anyway, so that's how you would demagnetize something, but it's all explained using the domain theory. Now the Earth itself also has a magnetic field, and it's somewhat for the same reason that a magnet would have a magnetic field. Okay? Inside the Earth, the molten core and the inner core, all made of iron. They're all made of iron. And the molten core is the key to the Earth's magnetic field. This molten iron is constantly in motion. There are actually currents in it, like there would be in the oceans. Okay? And because it's moving, because the metal is moving, this molten metal, then it can have, the domains can get lined up, and they tend to line up in the same direction. Okay, that is what creates, or at least that's the theory, of what creates the Earth's magnetic field. So it's almost like the Earth is a giant magnet. That's essentially what happens. And coincidentally enough, that magnetic field has changed direction several times in the Earth's geological record. If they go back and look at fossils, for example, and they look at naturally occurring ores that have magnetic properties, they can see how the dipoles are aligned different ways in different layers, which is evidence that the Earth's magnetic field has actually switched direction a number of times. Now, if you were used to using a compass for navigation, that could be bad news. All of a sudden the compass is not going to point in the right direction. Of course, we don't rely on a compass all that much anymore now that GPS has pretty much taken over. But anyway, that's the Earth's magnetic field. Right now, in modern times, it's kind of like a bar magnet. Now, what we call the North Pole, which is up here, that's actually a South Pole, because the north end of a compass is attracted to it, right? The north end of a compass actually points up here. That actually makes it a magnetic south. So it's kind of like a big bar magnet stuffed into the center of the Earth, but the South Pole is up here. Even though we call it magnetic north, it's actually a south magnetic pole. We call it magnetic north because the north end of a compass points to it. But like I said, in terms of a magnet, it would actually be a South Pole. And the Earth, it's interesting to note, actually has two sets of poles that are not exactly in the same place. For example, up here, there's a what we call magnetic north, and there's a geological or a geographic north. The geographic north is the end of the Earth's axis of rotation. Okay, that's fixed in place, doesn't move. Sometimes we call that true north. Okay, but the dipole, or the magnetic pole, sorry, is actually a ways away from that. It actually moves slightly over time because it depends on the way those currents are moving in the Earth's inner core, that molten core, or the outer core, I should say. All right, so it actually moves around a bit. And in fact, there's a number usually on a map. Maps that are used for navigation, for example, generally have a number on them called magnetic declination. And that tells you what the difference is between the magnetic pole and the actual geographic pole. So that if you're using it for navigation, you'll know that your compass is actually a little bit off true north, and you can actually subtract that from the readings to go in the right direction. Because the maps are based on true directions, not magnetic directions. So sometimes you'll need to correct for that. But like I said, most navigation now is done using GPS, so you don't have to worry about it. You don't have to worry about it. Anyway, moving on. Let's try some multiple choice questions. Okay, and these deal with what the magnetic field looks like around a magnet. Okay, you want to know the polarity of the magnetic field. Well, it turns out that magnetic fields around magnets, we can map those using a compass. So if we were to take a compass, for example, and bring it near a magnet, if the compass pointed away from the end of the magnet, if the north end of the compass pointed away from the end of the magnet, that would tell you that's a north pole. All right? Because like poles repel, that would make it point away. Okay? So what happens is the lines, the magnetic field lines, actually point in the direction that a compass needle would point. So if the lines are pointing from X to Y, that's telling you that this is a north right here. Because magnetic field lines are always drawn pointing away from a north pole and pointing towards the south pole. So that tells you that this is north, this is south. All you got to do is look at the direction of the arrows. That's it. So X is north, Y is south. The answer is B. That's simple. Okay, that's all you got to do. Look at the direction of the arrows. Kind of like the diagrams that we drew in another topic showing electric fields. Okay, when the fields go into each other like that, when they bend into each other, that is an example of a opposite. Sometimes we call it a dipole. Like for example, your magnet, okay, let's say this was a magnet. And if this was a north pole or a south pole here, this was a north pole over here, the magnetic field actually looks like this. We draw it out of here, it goes all the way around the magnet like that, and then back in right here. So it points away from the north into the south. So therefore up here it's actually pointing back that way. Same thing down here on the bottom. We could draw the same type of shape all the way around and back, away from the north into the south, which means it's pointing that way on the bottom. Okay, that's what the magnetic field looks like around a magnet. And we can tell that just by taking a compass and moving it around the magnet and watching the way the needle moves. So there's your answer, B. Let's try another one. A similarity between the Earth's magnetic and gravitational field. Well, field lines point only away from the Earth. Well, we know that's not true, right? If we looked at the Earth's magnetic field, right, here's the Earth, the magnetic field kind of looks like there's a giant magnet in it. So the magnetic field would look like this. Okay, it would point away here. Remember, that's where the north pole of a magnet would be, up this way, and then down this way. So obviously, they do not always point away from the Earth or towards the Earth. So these two are wrong. And then it says, field strength is dependent on distance from Earth. That's true. The farther away you get from the Earth, the weaker the magnetic field gets. Also, the weaker the gravitational field gets. So they both share that. That's common to both fields. Okay? It is dependent on distance. In fact, it follows an inverse square law. As you go further away, the field strength decreases by the square of the distance. So if you double the distance, it's 4 times weaker, for example. There you go. Now, which best represents the magnetic field around the bar magnet? Well, I just showed you that just a minute ago. Okay? Remember that magnetic field lines always go away from north towards the south. Well, away from the north, right, towards the south. So this one on top is right, but if you look on the bottom, this guy is coming the opposite way. Look, he's actually going into the north and away from the south. That's obviously wrong. Okay, this next one is obviously wrong because, again, they're opposite directions. See that? This one is pointing into the north, this one is pointing out. Not right. Right here, this one is pointing into the north, this one is pointing into the north, and on this one, out of north, out of north. So obviously, because the magnetic field lines always point away from a north pole, D is the correct answer. Simple as that. Try the next one. which is used to determine the direction of magnetic field lines around a bar magnet. Well, I just told you that a minute ago too. In order to get the field lines around a bar magnet, we use a compass. We use a compass. And more importantly, we use the direction that the north pole of the compass points. So it's a north magnetic pole that we use. The north end of the compass points in the direction of the field lines. That's what we use to determine the direction. We call that mapping the field. And a north pole of the compass is what we use to map a field. Okay, the next one deals with domain theory. It says which one of those would be the strongest magnet? Which one of those would be the strongest magnet? Well, remember, the strongest magnet is the one where the dipoles and domains line up the best. Well, obviously that's A, because in A they're all pointing in exactly the same direction. In fact, this would be a north pole, this would be a south pole, because those arrows of the dipoles always point to the north pole. That's what it would look like. Okay, B would be fairly close as well, because they're almost lined up, but not quite. Okay, C and D would be pretty weak because they're pretty random for the most part. They're pretty random for the most part. Okay, but the strongest one, definitely A. Definitely. All right, one more. We got a magnet that has been broken. We want to know the polarity, in other words, the north and south, what it would be at the break point. Well, because this magnet has a north pole at the left and a south at the right, that tells me that all my domains, all my dipoles, are pointing towards the north. Like that. So when I break that magnet in half, they're still going to point in the same direction. We still have to have a north on the left and a south on the right. Well, obviously it can't be A because I got two norths next to each other. That never happens. Not when you break a magnet. And D, the same thing. Two souths, not going to happen. Because the dipoles are all still going to be pointing to the left. So that means that the two halves that I have left over are going to have a north pole on the left of each piece and a south pole on the right of each piece. That's this guy. Right? North-south, north-south. We have to have two identical magnets left over when we crack it in half. So we knew it had to be either B or C, right? It couldn't be A because, look, north-south, south-north. That one's reversed, right? Same thing down here. North-south, south-north. This one here will be south-north, south-north. That's okay, but it's reverse of what it should be. Because if you look at the original magnet, the north had to be on the left, not on the right. That's why C is the best answer. That's why C is correct. Okay, so that covers magnets and magnetic fields. What we're going to look at in our next topic is we're going to look at the relationship between electricity and magnetic fields. Because there is a relationship. Okay? Flowing current, flowing electricity, moving electrons in other words, do create magnetic fields. And we already mentioned that in this topic, didn't we? When we were talking about domain theory, we said what actually causes magnetic fields in the first place is the movement of electrons around an atom. Okay? That actually creates a tiny magnetic field. So we're going to stop right here. Again, good luck with your studying. Be sure to come back and look at other topics. And study hard.